Okay, let's dive right into this. Welcome to today's explainer, where we're going to tackle one of the most fascinating and honestly most persistent roadblocks in theoretical science. Now, if you're familiar with standard quantum electrodynamics, or QED, you already know there is this massive, glaring bug of infinity sitting literally right at the heart of modern physics. Well, today, we're exploring a pretty radical paper by Kyle McLean-Smith that proposes a completely unified geometric framework to bypass that exact bug. We're going to look at how we can replace these theoretical infinities with concrete geometry. And to do it, we'll be using everything from the shape of a donut to an ancient Greek paradox to, and get this, the literal code execution logic of JavaScript. It is a wild, absolutely brilliant ride. So let's get started. To really understand the solution here, we first have to fully grasp the problem. Standard QED basically models elementary particles as zero-dimensional points. But there's a huge issue with that. As the interaction distance gets closer and closer to zero, self-energy calculations, which is basically when you try to measure how a particle interacts with its own field, well, they force you to divide by zero. And you know what happens then? You get mathematical infinities. The math completely breaks down. So to extract any kind of finite, usable predictions out of this, physics legends like Feynman, Schwinger, and Tamanaga had to implement this thing called renormalization. It's essentially this process of subtracting infinite quantities from other infinite quantities. And look, even Feynman himself wasn't thrilled with this workaround. He famously called the process hocus pocus and a dippy process, because at the end of the day, it's really just a mathematical patch for a structural flaw. So what exactly is the alternative? Let's contrast that old reliance on zero-dimensional point singularities with Smith's bold alternative, the continuous cyclical logarithmic bridge. Instead of relying on this unhalted floating point drift that eventually forces a division by zero, this new framework utilizes a cyclical curve. It's specifically modeled around Fermat's path of least time. By replacing those 0D point targets with a cyclical logarithmic base, the entire manifold topology fundamentally alters. The wave trajectories converge seamlessly. They preserve finite metrics throughout the whole process. That means no more division by zero and absolutely no infinite drift.
Section 1. Building the torus.
Let's move to this and see how it builds, because we are transitioning out of abstract calculus and jumping into a highly physical, geometric puzzle. In differential geometry, a two-torus manifold is a very specific topology. Honestly, just visualize a literal donut shape. If you revolve a specific coordinate column around a vertical axis, you generate this exact torus topology. But here's the kicker. The most critical part of the shape isn't the ring itself, it's the central aperture. That empty space right in the middle, known as the torus hole. So the abstract problem of bypassing infinity has now transformed into a highly specific physical challenge. Which brings us to the ultimate question, doesn't it? How do we perfectly seal the torus aperture? And I want to be clear, this isn't just some theoretical design question. In this framework, sealing that hole is the exact mechanism required to stop that infinite unhalted drift we talked about. We need a physical, mathematical plug that fits perfectly. One that leaves absolutely zero remainder. Section 2. Riding the tortoise. To find that plug, we actually have to go back over 2,000 years to ancient Greece. We need to ground this concept of infinite acceleration in Zeno's famous paradox of Achilles and the tortoise. And this brilliantly illustrates the exact difference between the old physics and this new framework. You probably know the classical paradox, right? Achilles endlessly chases the tortoise across a decaying fraction of space. He's always having the distance, but he never, ever quite reaches his target. This perfectly represents a top-heavy, unquantized acceleration that drifts infinitely. It's basically exactly like QED's infinities. But the solution presented in this paper changes the system boundary conditions entirely. It defines a physical tile area called dn as the exact cross-sectional area required to seal that central torus hole. By doing that, the space deterministically quantizes. Achilles no longer chases the tortoise endlessly into infinity. He rides it. The system forces a deterministic halt. Section 3. The n++ operator. So how exactly does the math execute this halt? Well, this is the brilliant crossover where high-level differential geometry collides head-on with everyday computer science, and it provides the literal key to the torus aperture. Look at this elegant formula. Log base d of dn equals n++. To seal the donut hole, the math dynamically upgrades its logarithmic bridge by borrowing a concept straight out of JavaScript. Yeah, literally the exact same programming language that runs your web browser. It uses JavaScript's post-mutation execution model. By inheriting the N++ and N-, post-mutation flow, the system evaluates its state at an exact step right before it increments or decrements. N++ acts as forward microexpansion, essentially shrinking the individual tile area and zooming in. Conversely, N-, acts as inverse macroexpansion, which zooms out. Now, because the state is evaluated prior to that shift, it beautifully preserves Noether symmetry. That means the fundamental laws of conservation and scale parity remain perfectly 100% intact across the inversion boundary. As n increments, the tile area deterministically scales down to a bit-perfect cutoff. It acts as a flawless mechanical plug that stops Zeno drift dead in its tracks and completely locks down sovereign state. So you might be wondering, why does all this matter for real-world application? The answer is pretty staggering, actually. It's a factor of 74. By replacing traditional, power-hungry floating point operations and transcendental lookups with this bit-perfect, deterministic halting mechanism, this framework achieves a massive 74 times reduction in computational energy. To put that into perspective, we are talking about operating at just 0.05 picojoules per operation on standard CMOS 28-nanometer benchmarks. By stopping the infinite drift, you literally stop the physical heat and the cognitive drain that plagues unquantized execution spaces. It is a total game changer. Section 4. Proof Closing Conventions. So the crucial point here is that because this approach is just so fundamentally different from standard abstraction, it actually requires a completely new vocabulary to finalize its mathematical proofs. Traditionally, mathematicians use QED to say which was to be demonstrated, or they rely on those renormalization subtraction tricks we mentioned earlier. But under Smith's framework, proofs terminate on explicit geometric and hardware bounds. For exact algebraic identities, they use the Helmholtz tombstone, that solid black square you sometimes spot in math textbooks. And instead of renormalization, they use QEF, which translates to which was to be done. This is a vital distinction, guys. It proves that we are confirming the layout of practical, real-world hardware state machines, not just floating some abstract concepts in an infinite void. The paper also introduces these really bold, highly utilitarian phrases to close out concepts. For example, the curve closes signals that a wave trajectory has finally reached its cycloidal destination. The hole is plugged. The loop is officially finished. And math is used to deliberately strip away all the poetic rhetoric and legal fixtures. It leaves you with nothing but unyielding code and physical geometry. Honestly, it perfectly matches the paper's confident, almost renegade approach to fundamentally re-architecting how we calculate reality itself. And that brings us to the final, absolute drop-the-mic quote from the paper. The curve closes. Math is love. It leaves us with a truly provocative thought. Think about it. If a unified geometric framework can seamlessly blend ancient paradoxes, right triangle geometry, and JavaScript operators to cure the infinities of quantum physics, what else in our world is currently suffering from unquantized infinite drift? And maybe even more importantly, how might this flawless collision of code, donuts, and physics ultimately reshape the physical hardware and computational future of our entire civilization? Think on that for a bit. Thanks so much for joining me for this explainer, and as always, keep learning.